Example 11. Evaluate the integral from e to the power negative x squared dx as an infinite series. Part B, evaluate the integral from 0 to 1 of e to the power negative x squared dx, correct to within an error of 0.001. Solution. First, we find the maclaurin series for f of x equals e to the power negative x squared. Although it's possible to use the direct method, let's find it simply by replacing x with negative x squared in the series for e to the power x given in table 1. Thus, for all values of x, e to the power negative x squared equals the sum from n equals 0 to infinity of open negative x squared close to the power n over n factorial equals the sum from n equals 0 to infinity of open negative 1 close to the power n times x to the power 2n over n factorial equals 1 minus x squared over 1 factorial plus x to the 4th power over 2 factorial minus x to the 6th power over 3 factorial plus ellipsis. Now we integrate term by term. The integral from e to the power negative x squared dx equals the integral of open 1 minus x squared over 1 factorial plus x to the 4th power over 2 factorial minus x to the 6th power over 3 factorial plus ellipsis plus open negative 1 close to the power n times x to the power 2n over n factorial plus ellipsis close dx equals c plus x minus x cubed over 3 times 1 factorial plus x to the 5th power over 5 times 2 factorial minus x to the 7th power over 7 times 3 factorial plus ellipsis plus open negative 1 close to the power n of x to the power 2n plus 1 over open 2n plus 1 close n factorial plus ellipsis. The series converges for all x because the original series for e to the power negative x squared converges for all x. Part B, the fundamental theorem of calculus gives the integral from 0 to 1 of e to the power negative x squared dx equals open bracket x minus x cubed over 3 times 1 factorial plus x to the 5th power over 5 times 2 factorial minus x to the 7th power over 7 times 3 factorial plus x to the 9th power over 9 times 4 factorial minus ellipsis on the interval from 0 to 1 equals 1 minus 1 over 3 plus 1 over 10 minus 1 over 42 plus 1 over 216 minus ellipsis, and that is approximately 0.7475. Sidebar, we can take c equals 0 in the antiderivative in part A. The alternating vector to text, the alternating series estimation theorem shows that the error involved in this approximation is less than 1 over 11 times 5 factorial equals 1 over 1320, which is less than 0.001, which is 1 over 1000. Another use of Taylor's series is illustrated in the next example. The limit could be found with L'Hopital's rule, but instead we use a series. Example 12. Evaluate the limit as x approaches infinity of e to the power x minus 1 minus x over x squared. Solution. Using the maclaurin series for e to the power x, we have the limit as x approaches 0 of e to the power x minus 1 minus x over x squared equals the limit as x approaches 0 of open 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus ellipsis close minus 1 minus x over x squared equals the limit as x approaches infinity of x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth power over 4 factorial plus ellipsis over x squared equals the limit as x approaches 0 of open 1 half plus x over 3 factorial plus x squared over 4 factorial plus x cubed over 5 factorial plus ellipsis close equals 1 half, because power series are continuous functions. Sidebar: some computer algebra systems compute limits this way. Multiplication and division of power series. If power series are added or subtracted, they behave like polynomials. Theorem 11.2.8 shows this. In fact, as the following example illustrates, they can also be multiplied and divided like polynomials. We find only the first few terms because the calculations for the latter terms become tedious and the initial terms are not the most important ones. Example 13. Find the first three non-zero terms in the maclaurin series for part A, e to the power x sine x, and part B, tangent x. Solution. Part A. Using the maclaurin series for e to the power x and sine x in table 1, we have e to the power x sine x equals open 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus ellipsis close open x minus x cubed over 3 factorial plus ellipsis close. We multiply these expressions collecting like terms just as for polynomials. You have 1 plus x plus 1 half x squared plus 1 over 6 x cubed plus ellipsis times x minus 1 over 6 x cubed plus ellipsis. Then we get x plus x squared plus 1 half x cubed plus 1 over 6 x to the fourth power plus ellipsis plus negative 1 over 6 x cubed minus 1 over 6 x to the fourth minus ellipsis. We have x plus x squared plus 1 over 3 x cubed plus ellipsis. Thus, e to the power x sine x equals x plus x squared plus 1 over third x cubed plus ellipsis. Part B, using the maclaurin series in table 1, we have tangent x equals sine x over cosine x equals x minus x cubed over 3 factorial plus 5 to the plus x to the power 5 over 5 factorial minus ellipsis over 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial minus ellipsis. We use a procedure like long division, where we have x minus 1 over 6x cubed plus 1 over 20 x to the 5th power minus ellipsis divided by 1 minus 1 half x squared plus 1 over 24x to the 4th power minus ellipsis. And I guess we multiply it by x. Okay, and then the next line is x minus 1 half x cubed plus 1 over 24x to the 5th power minus ellipsis. And what goes into there? 1 over 3x to the 3rd power. And then the next line is 1 over x to the 3rd power minus 1 over 30x to the 5th power plus ellipsis. I suppose that's multiplied by 2 over 15x to the 5th power. Anyway, we subtract 1 over 3x to the 3rd power minus 1 over 6 x to the 5th power plus ellipsis. Then you finally get the 2 over 15x to the 5th power plus ellipsis. Thus tangent x equals x plus 1 over 3x cubed plus 2 over 15 x to the 5th power plus ellipsis. Although we have not attempted to justify the formal manipulations used in example 13, they are legitimate. There is a theorem which states that if both f of x equals the sum from c sub n times x to the power n, and g of x equals the sum of b sub n times x to the power n, converge for the absolute value of x less than big R, and the series are multiplied as if they were polynomials, then the resulting series also converges for absolute value of x less than big R and represents f of x gx. For division, we require b sub not equal to 0. The resulting series converges for sufficiently small absolute value of x.